Well, as you're going to learn in Chem 1A, we're sacrificing one precipitate for another precipitate. When you have two precipitates competing, then we have to look at it deeper. And the deeper means which precipitate's more stable. Is lead-2 carbonate more stable or lead-2 sulfate more stable? And so we can't automatically say precipitation here because we're destroying one precipitate to form another. But one thing for sure we could say is going from a stronger acid to a weaker acid. Weaker acid would be this combination or a carbonic. Or we could say that we have a effervescence or gas formation. So stronger acid to weaker acid for sure, and effervescence for sure. All we need is one driving force, and then it should go. All right, what did you do for the ionic equation? This is what the CE. So if we say driving force, stronger acid, SA, weaker acid, so driving force, or gas formation. Some people write a little up arrow indicating that gas is being evolved. This formation, that would be the driving force too, or effervescence. For the ionic equation, do we ionize lead-2 carbonate? Leave it alone. We ionize sulfuric acid because it's strong acid. Strong acids, strong bases, and soluble salt.
So it's 2 hydrogen, 2H plus?
Yeah, well, 2H plus and sulfate.
Yeah.
Okay, there's some mixed opinion about this. Do both hydrogens break off sulfuric acid simultaneously? What do you think? Or one at a time?
That's 1 at a time.
It's one at a time. And so if the first one breaks off, then we're left with HSO4 minus. But is HSO4 minus a strong acid? HSO4 minus is borderline strong. If you look at the acid chart there, it's just short of being a strong acid. And so what happens is this is in water. In water, the first one breaks off, but the second one stays on in water. How do we get the second one to break off? The second one will come off when it's attacked, by lead. Lead's going to come in, knock that second one off, but it's not water. What we're looking at here is what's in aqueous solution, those H plus and HSO4 minus. Eventually, yeah, both of them are going to come off, but at this point, we're just looking at the major species in water. That's it. Okay, so this is very common error here, and this is going to form PbSO4. Do we leave that alone? H2O? Leave alone. CO2? Leave it alone. And so this would be it. Then we'd look for any spectators. Are there any spectators? No spectators. So this would be the CE, and the NIE and the IE are the same thing. What type of reaction is this? Metathesis. All right, let's continue our discussion of gases, liquids, and solids. We're looking at liquids. So what holds a liquid together? A lot of people think gravity holds, gravitational forces hold liquids together. So this is close to room temperature, 300 Kelvin. Just about room temperature. The water molecules are held together. You know what they're held together? It's not gravity holding the water molecules together, because a single water molecule doesn't weigh much. Since it doesn't weigh much, the gravitational force is pretty weak there. And so if you think, if you had, let's say, a pile of dust, and you blew on the pile of dust, the dust would scatter, right? It'd go into the air space. And so a pile of dust, each dust particle weighs way more than a water molecule does. And so what's holding the water molecules together are these attractive forces. The attractive forces you can see here in blue. We give certain names for these attractive forces here, but what happens is they form and they break. This is really slowed down, because if you look, this is in picoseconds, so that's 0.8889 picoseconds. And so this is really slowed down so that you can see the attractions here. Okay, so they get to a certain distance, and then these attractive forces will hold the water together. And the attractive forces, the strength of the attractive forces can play a big role in the physical properties of a liquid. So, for example, if the attractive forces are very strong, then what tends to happen is it's like glue. And it kind of resists flow, it becomes more and more viscous. And so if these attractive forces are very strong, it's like syrup. And then if the attractive forces are very strong, it's hard to boil. It's hard to vaporize off the surface. So we look at that. And so what's holding the liquid together are what we call intermolecular attractions. I saw another interesting simulation here. All right, so what we're going to do is we're going to look at these intermolecular forces in more detail. And that's chapter 15. So we looked at some properties already, but I'm going to come back to these properties in a minute. Vapor pressure. Vapor pressure is just how easily it evaporates. So, for example, if something has a very high vapor pressure, it evaporates easily. Therefore, it gets lots of liquid molecules in the gaseous state, creating a lot of pressure. So that's vapor pressure here. And so the weaker the attractions, the higher the vapor pressure, the stronger the attractions, the lower the vapor pressure. So we see here. So it depends on how strongly the water molecules are held. The stronger, the lower the vapor pressure, the weaker, the higher the vapor pressure. So water actually has pretty strong forces here, so the vapor pressure is not terribly high compared to something like alcohol. Alcohol has a lot weaker forces, and therefore it vaporizes much more easily. You'll get a lot more molecules in the gaseous state, creating collisions and pressure. We have to seal this, otherwise we'll never hit 100% humidity. Eventually all the water will evaporate. So that's why they cork it here. They cork it so that the air here becomes saturated with water vapor. And so we get 100% humidity, and then we measure the pressure. And that would be the vapor pressure at this temperature. If we change the temperature, we'll either have more molecules vaporize or fewer molecules. The higher the temperature, the more. The lower the temperature, the less. And so this is water. So alcohol weaker. Things that have stronger forces would be like syrup. Syrup has a lot of sugar and has pretty strong forces holding it together. The vapor pressure would be lower. There. Heat of vaporization is how much energy it takes to vaporize. So this again goes with how strong the forces are. We got to break all those forces. And so the heat of vaporization, the higher the heat of vaporization, the harder it is to break apart the molecules. The lower, the easier it is. And so water has a pretty high heat of vaporization, actually. Water's heat of vaporization is 44 kilojoules per mole, which is considered high. But we'll look at a number. You don't have to have that number memorized. Okay. Some things have a higher, even higher heat of vaporization, and some things have a lower. The boiling point, too. The boiling point, the temperature, which it spontaneously vaporizes. Water would be 100 degrees C. Some things have a higher. That is, they have stronger forces. Some things have lower, weaker forces. Boiling point. Turns out if it takes, for water, it takes 44 kilojoules per mole. 18 grams of water would require 44 kilojoules to vaporize. But when it recondenses back to a liquid, it releases all 44 kilojoules. It's a conservation of energy. And so energy input is equal to the energy output. So energy is neither created nor destroyed. And so we got to vaporize it. This is that boiling point here. You can see the water is boiling, spontaneously vaporizing here at this temperature, 100 degrees C. And so we break all of these. We got to completely break the water molecules apart and get them into the gaseous state. Once they're in the gaseous state, the distances are kind of big between the molecules, so there's not much attraction going on. Now we talked about viscosity. Viscosity is a resistance to flow. And so some things have a lower viscosity than water. The things that have a lower viscosity would be like alcohol. Those flow a lot easier. Versus things that have a higher viscosity than water, which would be like syrup, which would have stronger forces. So the higher the viscosity, the stronger the forces. And then we talked about surface tension. The surface tension of water, the water molecules are held together like glue. And so if you try to put a paper clip on the surface, it probably won't break the surface if you're careful. So we did that, right? The paper clip. You can do that too. And that is because the water molecules are kind of glued together. They can hold things on the surface. But of course, if you apply enough force, you'll break them apart and cause it to go in. We put soap in there. The soap screwed up the attractions between the individual water molecules. So this is surface tension here. Surface tension is usually talked about in terms of energy. In terms of energy, what we call a bulk or an interior molecule. Interior molecules here are surrounded by other water molecules. Water loves to be surrounded by water. And so this water molecule is very happy. However, the surface ones aren't as happy. The surface water molecules are only surrounded underneath, but above there's no water here. And so that makes them less happy. And so what we say is that the surface molecules have higher energy than the bulk molecules. This is why if you look at a water droplet will form what shape? If we look at a water droplet, a spherical shape. One thing about a sphere is a sphere is a shape with the smallest surface area per volume. And so a sphere, we're trying to minimize the surface area because the waters like to be around waters. And so the surface waters don't like to be surface waters. And so what will tend to happen is we'll beat up into big spheres. Unless, of course, there's something that water likes more than water. Is there something that water likes more than water? There is something that water likes more than water. You know what it is? It's glass. Clean glass. Water loves clean glass. So when you look at the inside surface here, the water is climbing up the walls. It likes, in other words, the glass is extremely polar. Water is polar. And therefore, light dissolves or light likes light. So light likes light, water likes glass. All right, so what we can see is here, let's look at the vapor pressure. The vapor pressure of mercury this is how many torr at 20 degrees C. 0.0012 torr is like nothing. And so mercury doesn't have much of a vapor pressure, but if you look at ethane, ethane's vapor pressure is 27,000 torr. Ether is 444.52 torr. Benzene 75. Water 17.5. And so if you look at this, you know, we see things with very low vapor pressure with very high. That means with high vapor pressure stuff, ethane has very weak attractions. Mercury has very strong attractions. In fact, mercury forms amazing spheres. Let me just show you this.
Like in science, you draw a little circle.
Where are those little circles?
Oxygen.
Are they just up?
Look at this. This is liquid. No, I didn't want to have. I don't have a good one. I should look this up a little bit. Well, you have a picture in your book of liquid mercury forming a nice bead. Basically, it's like this. You don't want to play with mercury, but if you have some mercury, what tends to happen is mercury likes mercury. It doesn't want to come into contact with anything else. So if you try to spread this out, it's just going to bead right back together. So mercury likes mercury. It doesn't like this paper. If we had some wax or something it really didn't like, it would form a ball, a spherical ball. So wax paper probably likes this is not working. It's just trying to minimize its contact. If you look at the bottom edges are curling up, you know, and the amount of mercury, well, it's got to fight gravity too, but the amount of mercury that's actually touching this surface is minimal. If you put the mercury on glass, it would be way better if they put it on glass. But, rather than this paper. Clean, very polar glass. Do that. All right. Well, anyway, that's
for vapor pressure. So things with very strong attractions, low vapor pressure. Things with very strong attractions will have a very high heat of vaporization here. So mercury has the highest, ethane the lowest. And things with the strongest attractions will have the highest boiling point, 357. So we look at the intermolecular forces here. Right, so we're going to name some. You know, for example, the intermolecular forces in water are primarily what we call hydrogen bond forces. But there are three main types that you should know. The three main types would be induced dipole, and hydrogen bond. We'll start with dipole first. That's the easiest to see. A dipole, you know, is two poles, a positive pole and a negative pole. So it's the interaction between positive pole of one polar molecule and the negative pole of another. So let's just take a look at dipole first. And so if we look at bromine chloride, BrCl, This is a diatomic molecule. Chlorine's more electronegative than bromine, so chlorine's going to have the negative end. This arrow points to the negative. Bromine's going to be positive, so the electron cloud's going to be pulled towards chlorine, polarizing the molecule. And so if we look at it, the negative end of this molecule will be attracted to the positive end over here. And this brown haze here is the dipole-dipole attraction. You know, obviously we can't see it. It's just an electrical attraction, but this will be attracted to that. The same thing here. Here we'll have a positive-negative attraction and negative-positive attraction. Here. And so bromine chloride, these are the forces that hold molecules together. One of the forces is to hold molecules together. Dipole, dipole.
So dipole interactions happen with anything that's polar. Like water. Water's polar. Since water's polar, we would expect a dipole-dipole attraction. So let's take a look at water. And so water is very polar because of these polar bonds, and they aren't canceled because of the bent structure of water. Water, though, is very unusual because its dipole attraction is so strong that they call it something else. They call it hydrogen bonding because the dipole attraction is so strong. So it has an unusually strong dipole attraction. There are other things with unusually strong dipole attractions too. So we can see it here. This is a little bit confusing, but here, ammonia has very strong attractions. This is the boiling point. So we look at the boiling point. Boiling point of water is 100. The boiling point of ammonia is actually pretty low. Ammonia is normally gas, but it's higher than what's expected. Because if we look at this, what we're seeing here is stronger dipoles. So for example, tellurium, H2Te, versus selenium versus sulfur. Which one's more electronegative? We look at the periodic table. Looking at the periodic table, if we look at tellurium versus selenium versus sulfur, which one of these three is most polar? I mean, has the most electronegativity? Tellurium, selenium, or sulfur? Sulfur. Sulfur is the most polar. Okay, then let's add oxygen. So we got tellurium, selenium, sulfur, oxygen. So oxygen-hydrogen bonds will be the most polar. So let's look at the trends here. So we're just going to look at this first red line here. What's happening is we're going from H2Te to H2Se to H2S. And what's happening is it's becoming more and more polar. But something weird's happening because as it becomes more and more polar, you would expect the dipole attraction to get stronger. And so what's happening is the dipole attraction is becoming stronger, and yet the boiling point's going down. We expect if the dipole attraction gets stronger, the boiling point should go up. Because the bigger the dipole, the stronger the electrical attraction. But here what we're seeing is that the bigger the dipole, it's not working. However, if we look in this box here, germanium, arsenic, selenium, if we look at germanium, arsenic, selenium, selenium is the most electronegative. And so when we look in this box, it works because the most polar will be H2SE. And so here we see polarity. As polarity increases, the dipole increases. As the dipole increases, attractions increase. Attractions increase, the boiling point increases. That works there. And so we expect this to happen. What should happen is H2O should be down here. H2O should be around, let's say here, but H2O is way up there. And so something weird happens with H2O, something weird happens with NH3. Okay, so there are a couple of trends here that are hard to see in this chart. Let's see if we can figure it out. One of the trends is this. Why is it that the stronger the dipole, the weaker, as we go left to right here? However, as we go up and down, the stronger the dipole, the stronger. And what it has to do is with the size of the molecule. So, for example, the bigger the molecule, tellurium, the bigger in terms of mass or electrons. If we look at the periodic table again, it has to do with electrons. Has to do with electrons. Sulfur has 16 electrons, selenium has 34 electrons, tellurium has 52 electrons. So tellurium has a total of 52 electrons. And so that's why tellurium has a much higher boiling point in this particular diagram. Tellurium has 52 electrons, and so what's happening here is this. What's happening is something called induced dipole. Instantaneous induced dipole. So this is it, 1511. Induced dipole forces. So if we have two atoms, or molecules, this is two nonpolar, but it doesn't have to be nonpolar, it could be polar as well. What happens is sometimes the cloud can be distorted. So for example, if the electron were up here, not down here, then that's what we call an instantaneous dipole. So let's say this had 52 electrons around here. And let's say, out of that 52, we have more electrons here than here. So out of that 52, let's say 30 are here, and 22 are down here. That's going to create a dipole. That dipole is not going to last very long because pretty soon the electrons are constantly moving. So the dipole will disappear. But in that instant that dipole exists, it'll induce a dipole here because the electrons here will see the negative charge here. If they see the negative charge here, they'll run away from the negative charge. They'll move to the other side. But if the electrons ran away, they move to the other side. Not all of them. And that induces a dipole. Now we have what we call an instantaneous dipole attraction. This instantaneous dipole attraction lives just for a moment in time. But this is how nonpolar molecules or atoms can attract one another. And so, for example, what attracts mercury to each other? Well, one way mercury can be attracted to each other is mercury can be attracted to another mercury by electrical forces. But when you look at it, all the electrons are in their shells. And when they're in their shells, they have this spherical symmetry. But the electrons are constantly in motion. So if these are two mercury atoms, how many electrons does mercury have? Let's take a look. The more electrons, the better. Why the more electrons, the better? Mercury has 80 electrons. The reason why the more electrons the better is because it's easier to distort the cloud. And we can generate much bigger dipole, instantaneous dipoles. So if you have 80 electrons, normally the 80 electrons are evenly distributed in the shells here. But in one instant of time, you could have a few extra electrons on one side. If you have a few extra electrons on one side here, it creates an instantaneous dipole. It induces a dipole, and then we have an attraction like this. Then the electrons move, and this breaks, and it's no longer there. And so this is one way mercury can be held together. Two mercury atoms can be held together. They're held together by electrical forces. And so let's see if we have a video. go. Instantaneous induced dipole. So we'll take a look at this. These are also called London dispersion forces. Let's see if we have a simulation, which would be better. Oh, I guess that's about it. I had a great simulation, but it was on video. Cassette. Unfortunately, we don't have video cassette anymore. Okay, these are called London dispersion forces. I don't know why, but he's probably talking about why they're called London dispersion forces, but I don't want to see all 5 minutes of this. I'm going to fast forward this. That's probably Fritz London. It's probably the person who developed the theory behind this.
Between this molecule and this molecule, between this molecule and that molecule. And these are generally going to be really, really low compared to the intramolecular within the molecule itself. And we'll talk more about those in later videos. But London dispersion forces are going to be attractive forces. These are intermolecular, between molecules. They're going to be found in all atoms and molecules. Everything is attracted through London dispersion forces. Really important. What are going to be found in all atoms.
Yeah, this is really important because they said between two nonpolar.
That's actually wrong. London forces happen between everything. Everything that has electrons, which is everything. And so as long as it has electrons, then London dispersion forces are at play.
So that's really important. That's good.
Atoms and molecules. Everything is attracted through London dispersion forces. Really important. What really develops them are uneven electrons. As the electrons are distributed unevenly, they create what are called a temporary dipole. Those are going to be a molecule that has a charge. It's a positive and a negative charge. These are going to increase as we increase the contact area between the molecules. Also, as we increase their polarizability, which is going to be the squashiness of a molecule. Normally, the more electrons you have, the higher this is going to be. And so as we increase molecular size, we're going to increase these dispersion forces. And finally,
Okay, polarizability is the cloud. You know how fluffy the cloud is or how easy it is to distort the cloud. Something with an easily distortable cloud is highly polarizable. That is, you can easily change the cloud shape. Things with a tightly held cloud, electron cloud, are much less polarizable. And so some people say, easily polarizable is soft, something that's not easily polarizable is hard.
pi bonding, which is going to be where orbitals overlap. If we have more pi bonding, we're going to increase those. And so let's look at why are London dispersion forces important? Well, they're in everything. And if it weren't for them, we'd never have noble gases in a liquid phase. And we know we can do that if we can cool it down. And so what holds helium together when it gets into this liquid phase? It's going to be these London.
Yeah, right. This is liquid helium here.
Liquid helium is at 4 Kelvin. So if you have liquid helium here, what's holding the atoms together? Not gravity, that's for sure. Not gravity.
Well, what's holding them together? London dispersion forces, or instantaneous induced dipole, or induced dipole. Our book calls them induced dipole.
Dispersion forces. So right here I have 2 helium atoms, and so they're going to have 2 protons on the inside, 2 electrons on the outside. And so as we move them close together, watch what happens to their electrons. Let's watch that again. As they move close together, the electrons are going to migrate. What's doing that? Well, the electrons on the outside of one helium are going to be attracted, it just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside. So what this really is creating are 2 what are called temporary dipoles. They have positive and negative ends. So a London dispersion force is simply going to be the connection between those 2. It's fairly simple. It's going to hold them together. Now it's just temporary and then it's going to go away. But if we have enough of these atoms in an area and it's cool enough, then we can get it. So what's going to increase these London dispersion forces? Well, contact area is one thing. The more electrons we can have closer to each other, the more of these forces we're going to find. So if we look over here at N-pentane and neopentane, they're both going to be made of the same atoms. But these ones right here are going to be looking more like a column and these more like spheres. And as a result, these ones are going to have more surface area, more contact area, so we're going to have greater forces. And so the boiling point of N-pentane is going to be higher than that of neopentane based on these London dispersion forces. What else? The polarizability. Polarizability, remember, is the squashiness. The more electrons we have, the more forces we're going to have. And so this right here is a protein. Proteins are massive in size, and a lot of that three-dimensional shape comes from these London dispersion forces. Also, it's going to explain why, as we go down in the periodic table, let's look at the halogens right here. Halogens are going to have the same valence electrons, but as we go to fluorine, chlorine, bromine, and iodine, we're actually going to go from gases, fluorine, chlorine, to liquid bromine, and then solid iodine. And that's all going to be based on these London dispersion forces. As the atoms get bigger, they have more electrons, we're going to have more of this uneven electron. And then finally, pi bonding. That's where we're going to have orbitals that overlap and form something called a pi bond. If we increase the number of pi bonds inside those molecules, we're going to increase these London dispersion forces. So again, what are they? They're attractive in nature, found in everything. It's uneven electrons create these temporary dipoles. Remember, what increases it, our list would be contact area or surface contact. Also the polarizability, which is going to be based on the molecule size, and pi bonding. Can you do that? Could you explain these trends? If you can remember those three things, you've got it, and I hope that.
Can you guys hear this, or is this too low? Too low. Get one little higher out of it.
In a microwave oven, an electronic vacuum tube called a magnetron produces short radio waves called microwaves. In most such ovens, these waves travel through a waveguide, a rectangular metal tube, to a stir, a fan-like device that scatters the waves around the metal interior of the oven. The waves bounce from wall to wall until they enter the food. Water molecules, which are contained in most foods, are dipolar. That is, they have a positive electrical charge at one end and an equal negative charge at the other. These dipolar molecules act as tiny magnets, and as microwaves pass into the food, the molecules are pulled first one way, then the other, by a magnetic field created by the waves. This back and forth motion of the molecules molecules occurs nearly 2.5 billion times a second. This rapid vibration causes friction between the water molecules, which produces heat.
Thank you. Okay. That was just a little bit for water. So let's take a look at the. We'll come back to that, but let's take a look at this.
So it turns out that those instantaneous dipoles are very important. And so what we can do is if we compare things of greatly different mass, let's say if we compare something like bromine here and ICL, these have very similar mass, but if we look at ICL versus something like CO, these have very different mass. And the mass is going to be related to how many electrons. And so if we look at the molecular mass, the greater the molecular mass, the greater the number of electrons. And so what typically happens is this: as the molecular mass increases, the boiling point also increases. And that's because of the instantaneous dipole. Now, if you add to that polar, like a permanent dipole, then we'll have more. And so let's take a look at this trend here. The trend we're going to look at is HI versus HBr versus HCl versus HF.
So when we analyze these, the first thing we look for is there a dipole,
A permanent dipole. And there's a permanent dipole here. For example, fluorine's more electronegative than hydrogen, so it's going to pull the electron cloud towards it. So you have a dipole here. However, HI also, iodine would be more electronegative. HI, we'd expect a dipole too, but the dipole will be a lot smaller. The dipole is going to be a lot smaller because iodine is not nearly as electronegative as fluorine. And so what happens here is this. As we go down this list, the polarity increases. As the polarity increases, then we get stronger dipole attractions. And so the species with the strongest dipole attraction will be HF. The species with the weakest dipole attraction will be HI. And so based on dipole attraction, we expect HF to have the highest boiling point, HI to have the lowest boiling point. This is based on dipole attraction. And so let's take a look. Let's take a look at the data. And what the data shows is that the species with the highest boiling point is HI. So the boiling point increases this way. And so the highest boiling point is HI. That means HI has the strongest attractions holding the molecules together. Strongest attractions. And then HF will have the weakest, because this will have the lowest boiling point. It's going to have the weakest attractions. And so this is what we predict. This is what's observed. And so what it boils down to is this. The reason why HI has the highest boiling point, even though it's the least polar, and it's going to have the weakest dipole. It's because of the instantaneous dipole. And so we have something like this. If we look at HI, this would be the average dipole. And then we look at HF, this would be the average dipole. Okay, then we look, well, how many electrons does fluorine have versus iodine? And so going back to the periodic table, you can see that fluorine has 9 electrons here, but iodine has 53 electrons. So 9 versus 53 electrons means this. Iodine has 53 electrons plus the hydrogen, and so the total number of electrons will be 54. HF, the total number of electrons will be 10. And so which one's more polarizable, having 54 electrons or 10 electrons? Which one's going to have a bigger cloud? 54 electrons. And so what happens is the average, well, what is the average? The average is between extremes. And so what happens is sometimes the dipole is non-existent versus sometimes it's huge. And so let's say all 54 electrons move to the right side. If all 54 electrons move to the right side, then we're going to get an enormous dipole like this. Or the electrons balance out, or if they move to the left side, the dipole will be shot in the other direction, here. Whereas HF, HF, the extremes are going to be like this. And so what happens with HF is it doesn't have that many electrons, so the average is tight around here. So sometimes it's a little bit bigger, sometimes it's a little smaller, depending on how the electrons fluctuate. Whereas HI, there's so many electrons, the fluctuations are going to be huge, because you have 54 electrons now. And so the instantaneous dipoles can be enormous. So an instantaneous dipole of 1 second is like this big, and that's going to generate a huge dipole attraction. Versus with HF, that's only got 10 electrons. Yeah, on average, it's bigger, but it doesn't swing as much. Does that make sense? And so, in other words, we have to consider this. When we're looking at the dipole, we're looking at the permanent. When we drew the dipoles for the molecules in Lewis structures, those were the averages of the permanent ones. We don't look at how those fluctuate over time. And so if we look at how they fluctuated, then we're going to see things with a large number of electrons are going to have huge dipole fluctuations, which is going to result in strong attraction. And so the reason why that HI has a much higher boiling point than HF is because of the much stronger dispersion forces, or London dispersion forces, between the HI molecules. And so this is why we have a chart like this. Let's take a look at this chart in a little more detail here. What they're trying to do is they're trying to keep the dispersion forces roughly the same. So if we compare nitrogen and carbon monoxide, the dispersion forces are going to be roughly the same because they'll have the same number of electrons based on the molecular mass here. And so what we see here is that this. Nitrogen is nonpolar, carbon monoxide is polar. And so if the dispersion forces are the same, then carbon monoxide should have a higher boiling point. That's not much difference, but carbon monoxide does have a higher boiling point because of the dipole forces, permanent dipole forces. Here we're looking at silane, or silicon tetrahydride, versus phosphine, or phosphorus trihydride. Here, the dispersion forces are roughly the same, 32, 34, roughly the same. But phosphine, or phosphorus trihydride, is much more polar, so it's going to have a higher boiling point. So the more polar it is, the higher the boiling point, as long as we keep the masses the same. So nonpolar versus polar, polar is going to have a higher boiling point as long as the masses are about the same, or dispersion force is about the same. Non-polar versus polar. Polar is going to have a higher boiling point. So polar has a higher boiling point. That's the take-home message from this. However, we have to even the playing field. That is dispersion. Now, if we don't keep the playing field even, then the dispersion wins out. That's what happens here. So, if we keep the playing field even, the dispersion forces are all about the same because all these have roughly the same molar mass. They have roughly the same number of electrons. And so, if all these have roughly the same dispersion, then the difference is polarity. Germane, GH4, is nonpolar. This is more polar, arsenic trihydride, or arsine, and hydrogen selenide is the most polar. And so the stronger or the more polar the molecule, the higher the boiling point, as long as the dispersion are the same. But if we start to change the dispersion, then dispersion wins out. So for example, H2T is the least polar, H2SE is more polar. And so this is more polar, but this also has a lot more electrons. And since this has a lot more electrons, the dipole can fluctuate over a much wider range. H2S, this is even more polar, but fewer electrons. So I think I got that mixed up. So this has the most electrons, so the dipole can fluctuate over a wide range, even though it's not very polar. This is the most polar. However, it doesn't have very many electrons, so it isn't very polarizable compared to H2TE. So that's right. But H2O is the most polar, and it's also got the fewest electrons. And so here, dispersion didn't win out. Here, this is why it's unusual. Here, if dispersion were to win out, then yeah, it's the most polar, but since it's not very polarizable, it should fall right about here. But it falls way up here. And so we call this an unusually strong dipole. This unusually strong dipole happens when hydrogen's bonded to oxygen, hydrogen's bonded to nitrogen, and hydrogen's bonded to fluorine. If you look at methane, methane follows the trend. In fact, this is a nice trend showing dispersion forces because methane, silane, germane, and stannane, these are all nonpolar. So methane's the lightest with the fewest electrons. So the tin has the most electrons, being the most polarizable. It's a little bit confusing because tin tetrahydride is also the heaviest, but it's not gravity that holds them together. It's the attraction. All right, so these are unusually strong dipole attractions when hydrogen's bonded to nitrogen, hydrogen's bonded to oxygen, hydrogen's bonded to fluorine. These attractions here we call hydrogen bonding attractions. Those are unusually big. So two waters will be hydrogen bonded to each other. Methanol is also going to be hydrogen bonded because of the HO bond here. This is methylamine. So anything with HN bond, HO bond, or HF bond will be hydrogen bonded. So you expect large boiling points for that. All right. What happens is if I have water at 25 degrees C, we're going to look at the vaporization process. So we're veering away from intermolecular attractions. Looking at water at 25 degrees C, are all water molecules in the sample moving at the same speed? No. In fact, what we see is we see a distribution. This is called a thermal distribution, Maxwell-Boltzmann distribution. And if we look at the water molecule distribution, some are moving slow, some are moving very fast. Some are moving so fast that there's a cutoff here. This cutoff here is the amount of energy required to vaporize off the surface. And so this is the number of molecules having enough energy to evaporate for this pink region here. These molecules down here don't have enough energy to evaporate or vaporize. So at room temperature, there's a small fraction of molecules that can vaporize off the surface. So let's take a look at the liquid-vapor equilibrium. We call this a dynamic equilibrium. And what happens here in this dynamic equilibrium? Dynamic means change, equilibrium means no change. So I talked about this before. Did I talk about this before? No? All right.
You see this chart?
We've seen this before, yeah. Initially what happens is we have evaporation. This is dry air. And as the evaporation continues, we get more and more water molecules into the gaseous state. And sometimes these water molecules can come back down and strike the surface. When they strike the surface, they might get stuck, like glue, with the hydrogen bonding interactions. They're hydrogen bonding and dispersion forces holding water molecules together, but primarily it's the hydrogen bonds that are most important. But here, we got much more evaporation than condensation. And so the evaporation continues, and it continues to build up more. And so the relative humidity is increasing. Maybe this is 50% relative humidity. So here, the condensation rate's increasing. Condensation rate's going to depend on how many gaseous molecules we have. Eventually, we'll have so many gaseous molecules in here that the condensation rate equals the evaporation rate that's happening here. And so what happens is the condensation rate equals the evaporation. The evaporation rate kind of just stays constant. It just depends on temperature. Condensation rate depends on how saturated it is. Once we hit 100% relative humidity, then there's no more net change. And this air is saturated with water vapor. And so since there's no more net change, we hit 100% humidity, it stays at 100% humidity. It doesn't change from there. And so that's what we call equilibrium. There's no change. However, it's dynamic because evaporation and condensation never stop. And so there's always change, but there's no change. There's change at the molecular level, there's no change in the macroscopic level. So this is liquid vapor equilibrium. Okay, this is vapor pressure. Mentioned water has a fairly high vapor pressure. This is vapor pressure with temperature. And so what happens is this: as we change the temperature, we're going to change the humidity. How that happens is this curve here. The area under the curve stays the same for a water sample. If we increase the temperature, what happens is this curve shifts to higher energy. And that is, this part flattens down and this part grows. So what will happen at higher temperature is we'll get a larger fraction of molecules that can evaporate off the surface. At lower temperatures, this whole curve shifts left. And so at lower temperatures, this grows here, and then this higher end shrinks down, so we'll have a smaller fraction. And so temperature is going to change the fraction of molecules that can evaporate. So you can see this in a graph here. It's nonlinear, this change. And so at low temperatures, not much vaporizes. And so this is the pressure generated by the gas molecules, gaseous water molecules. As I increase the temperature, I get more and more gas molecules at one. This is all for 100% relative humidity. An interesting thing happens because if I increase the temperature to 100 degrees C, then the vapor pressure hits 760 millimeters of mercury. Well, 760 millimeters of mercury is what we call atmospheric pressure. And so when the vapor pressure equals the atmospheric pressure, then you have the vapor pressure pushing up, the atmosphere pushing down. They're equal and opposite. What we're going to have is boiling. And so this is what we call the normal boiling point. The normal boiling point is the temperature at which the vapor pressure equals 1 atmosphere. And so the normal boiling point for water is 100 degrees C. The normal boiling point for ethanol is lower, 78.3. Ethanol has a higher vapor pressure, you can see here. And so at 20 degrees C, there's pretty much nothing for water. It's very low. But for ethanol, there's already significant vapor pressure. This is not zero here. This line should continue out here. It's just very low. It's for ethanol. Ethanol is very what we call volatile. Diethyl ether is even more volatile. Diethyl ether boils at 34.6, which is close to room temperature. You got a very high vapor pressure. Oh, yeah, okay. Here's what we're talking about.